So I was a little worried that we would run out of time in class to talk about all the things that I wanted to talk about. So I'm going to just so I made some videos. I guess I'll tell you in class. Anyway, so this first video is going to be about the pigeonhole principle. So applications of the pigeonhole principle. So this is the thing that I stated in class. It said that so if you have 20 pigeons in 10 holes, it's impossible to stuff all the pigeons inside the holes without having two pigeons in one of the holes. So the pigeonhole principle. Hole. So, well, you can't, if n is greater than r, and you have n pigeons and r holes, you can't stuff the pigeons into the holes without duplication, without having at least two pigeons. In some hole. Okay, so the mathematical statement is about injections, and it says that if n is bigger than r, then there does not exist. So contrary to infinite says there does not exist an injection f from the larger number of pigeons to the smaller number of holes. You cannot inject into the pigeons into the holes. So here we're using the notation that we've been using, that n sub m for a given natural number m is just the set of the first m natural numbers. Okay, so I want to give you the applications of this thing are pretty cool. Okay, so here's the first application. Okay, so so for any 5 numbers in a 1-by-1 box, or any 5 numbers in a 1-by-1 box, so like a kind of a square with side length 1, there exists a pair of these 5 numbers within distance square root 2 over 2. Okay, so here's the proof. It's so the name of the game with all these proofs is that we divide. So we divide the problem into pigeons and holes. So the pigeons are the numbers. So let me draw the box here. Okay, so here's 1, and here's 0, and here's, so like here at the starting point, this is the point 0, 0, and this is like the point 1, 0. Okay, and so this also has side length 1, so maybe this is 1, 1. So so we can partition the box into 4 holes, and then if we took 5 random numbers here, so any 5 like this, okay, there's going to be 2 in a given box. So here the given box is this one that we drew. Okay, so this, and then the maximum distance between, let me see if we can do it, between the largest distance here, well, this side length is side length a half, and this is side length a half, so this hypotenuse here is a half squared plus a half squared, and we take the square root of this, and so this is equal to, well, this is 1/4 plus a fourth, and so this is equal to the square root of 2 over 4, which is square root 2 over 2. Okay, and of course, in doing the proof, if we were going to write this out rigorously, you'd have to say more words and things, but this is a video, so I'm just going to leave it at that. But this is the idea, okay? So like the pigeons were the points, and then the holes were these 4 holes here. So you have 5 pigeons and 4 holes. They don't match up. All right, so we can continue with this. Okay, so let me give you another application. Here's the second application. Okay, so any subset of this thing, 1, 2, all the way up to 9, so this is n sub 9, of size at least 6 contains a subset. So a subset of the subset whose elements add to 10. Okay, so here's the idea. So like if I take a subset here, S, right, then I can find I can find another subset of S where the elements add to 10. Okay, so here's the proof. Okay, we observe that so we observe that, you know, the pairs, 1 plus 9, 2 plus 8, 3 plus 7, and then 4 plus 6, these things all add to 10. Okay, you can't do 5 plus 5. Those, so these guys, so we observe these pairs. Okay, and so if we pick 6 elements, one of these pairs must be included. All right. So what are the pigeons and what are the holes? So I guess the pigeons are the pairs, like 1, 2, 3, 4, or sorry, the pigeons are the 6 elements, and the holes are the pairs. So the pigeons. So this one you kind of have to think about backwards are the numbers, the 6 elements, and the holes are the pairs that you're trying to avoid. Okay, so here there's only well, I guess there's 5 holes. So if you include the 5th guy, so you can pick one of each of these. You can pick 1 or 9, 2 or 8, 3 or 7, 4 or 6 or 5. Okay, so there's 5 holes, but you have to pick 6 things. Okay, and because you have to pick 6 things, there's going to be there's going to be one there's going to be one of these pairs that has to be included. Okay, one of the pairs must be included. and then we can say by the pigeonhole principle. All right. Okay, so let's do another application. So I think I've all right. So here's a third application. So for every subset of n plus 1 integers from 1 all the way up to 2n, there exists a pair of coprime integers. Okay, so this is like if I take 100, if I consider the numbers 1 through 100, and I take 51 numbers in between 1 and 100, then there's going to be 2 of those numbers are going to be coprime. Okay, so the trick is that 2 consecutive integers are coprime. Okay, so this means that if I take n and n plus 1, they're coprime. So to be coprime, this is the same thing that there doesn't exist a prime such that the 2 numbers are both congruent to 0 mod p. So if n is congruent to 0 mod p, then n plus 1 is not going to be congruent to 0 mod p because n plus 1 is going to be congruent to 1 mod p. Okay, so how to do this? So okay, the 2 consecutive integers are coprime, and so there exists 2 consecutive integers in any given n plus 1 element subset. Okay, so the holes here, or let's say the pigeons. So these are our n plus 1 elements, numbers, and the holes. So these are going to be the set of even numbers, or the set of odd numbers. So anytime you have if they're not going to be consecutive, given a number, the adjacent number needs to still be even or odd. Okay, and so if you were to fill them up, the best you could do is like put all the even numbers, but there's only 50, or like say if the number is 100, there's only going to be 50 of those, and the 51st spot is going to go into one peg, and then there's going to be going to go into one of the holes in between the adjacent ones. Okay, so there's actually going to be, I guess, 3 consecutive integers. All right, which is kind of cool. So you get to prove something stronger. Okay, let's do application 4. Okay, so for any n plus 1 element subset of the set 1 through 2n, there exists a pair AB in the set where A divides B. right. This is much trickier, okay? So the idea here is that so I'm going to make pigeons and holes. So the pigeons, so these are our n+1 elements. And the holes, so these are certain sets A, I, let's say A, B. Okay, so for B an odd number, so for B odd and less than or equal to, or less than 2n. So let's say what AB is. AB, so these are the sets of 2 to the I, B, so where 2 to the I, B is less than, so I is an integer, is less than 2n. Less than or equal to 2n. Okay, so for example, if n, so if n was equal to, or 2n was equal to 18, then A1 would be 1, 2, 4, 8. A3 would be 3, 6, 12. A5 would be 5, 10. Okay, A7, 7, 14. A9 would be 9, 18. Okay, A11 would be just the set 11. A13 would be just the set 13. Then we have A15 would be just the set 15. A17 would be just the set 17. Okay, and so on. Or I mean, not and so on. So these would be all the sets here. So 2n would be 18, so n would be 9, and so we would have these 9 subsets. Okay, since we have 9, so we have more than these. So we have 10 elements, right? n+1. There would be one that would have to occur in 2 of these. All right. So if we have 2 elements, in one of these, so notice that if we have 2 elements, 2 in some here, A, B here, so this is the set of 2 to the I, B, for, I such that 2 to the I, B is less than or equal to 2n here. Then we'll have, so then one will divide the other. So we have, 2 to the, let's say 2 to the A1B and 2 to the A2, 2 to the A1 plus, I don't know, something, CB. And so, okay, so these guys here are an AB, and this thing, 2 to the A1B, divides 2 to the A1 plus CB, because this is really 2 to the A1B times 2 to the C. Okay, so this is how we get the divisibility. That's kind of a cool trick. All right, so this is one way to do this. So this is a trickier way of cooking up the holes in the pigeons. All right, so there's another cool statement that we can do. So this is about irrational numbers and approximating irrational numbers. So what application are we on? We're on application 4. Application 5 is the following. Okay, so if alpha is a real number, is irrational. So this says that you can arbitrarily approximate irrational numbers by rational numbers. So then there exists infinitely many P over Q in Q such that alpha minus P over Q is less than or equal to 1 over Q squared. Okay, so there's a bunch of theorems around approximating irrational numbers by rational numbers. So there's other theorems that you could look up called Dirichlet's theorem and Louville's theorem or Louvie's theorem, Louvier, and then and so you can look up, and there's another big theorem. It's called Ross theorem. Anyway, this is kind of a thing mathematicians like to do. They like to approximate irrational numbers by these, and the degree of approximation can kind of tell you about whether or not it's transcendental, meaning it doesn't satisfy a polynomial equation, or whether it's algebraic. And remember, we talked about algebraic and transcendental things, and most numbers are transcendental. Anyway, we can prove something like this using the pigeonhole principle. Okay, about approximation of irrational numbers by rational ones. Okay, so we can do, here's the proof, and what we'll do is so this is where the infinitely many comes in, so we can fix Q arbitrarily large and arbitrarily large integer. Okay, and we will produce some P over Q such that alpha minus P over Q will be less than 1 over Q. Okay, so this is where the infinitely many part comes in, is because I'm gonna start with this Q and I can modify this Q if I want. Okay, but anyway, let me show you how to do this. So first, what we'll do is we're gonna break up the interval 0, 1 into wholes. So we break up the interval 0 to 1 here into intervals. Okay, so what we'll do is we do, so here's 0, and here's 1 over Q, and then we can do 1 over Q, and then we can do 1 over Q to 2 over Q, and then we can do 2 over Q to 3 over Q, and so on. Okay, so we break this up into Q, so eventually we get to 1. So this will be Q, Q wholes here. Okay, let me just copy this over to the next page and I'll show you this. So here's our number line, 0, 1. Okay, and then we chop this up. Okay, into so we chop into Q intervals. Okay, and then what we'll do is we'll consider. Let me just do some notation real quick. So for X and R, this thing here will be the fractional part. Fractional part of X. So this is this notation. So for example, 3 halves. So this is equal to 1 plus a half, and this is equal to a half. Okay, so you just take like the part that's smaller than 1. So you kind of take off the biggest integer that you can. Okay, 0, 1. All right, and then what we do is we consider, so we have 0, and then we have Q, or so we have 0, alphas are our irrational number, 2 alpha, 3 alpha, okay, all the way up to q alpha. Okay, so this is a q plus 1 elements of the interval 0. So if this is a whole number, we'll say that the fractional part is 0. The interval 0 to 1. Okay? So we have it something like this. Okay, so since there's q plus 1 elements, so they'll be distributed something like, I don't know. But eventually, there's going to be one spot with 2 holes here. Or, sorry, one hole with 2 pigeons. So there's going to be some 2 of these guys which are going to be in the same spot. So we're going to there exists. So by the pigeonhole principle, pigeonhole, one word. There exists some Q1 and Q2 with these things here. So 0 is less than or equal to Qi is less than or equal to Q. And these things are distinct such that Q1 alpha and Q2 alpha are in the interval S over Q, S plus 1 over Q. So this is all in the numerator. For some S. Okay? So S is also going to be in here. S is going to be in between 0. S is an integer. S is going to be in, this is going to be Q minus 1. Okay? So it's going to be in one of these things. So here would be, here's S over Q, and this is going to be S plus 1 over Q. This one here, and this one here. And then in this interval, there's 2 of these guys. So this is going to be the fractional part of Q alpha, fractional part of Q1 alpha, and the fractional part of Q2 alpha. Okay? So note that now that we have this, if we let, so we're going to let Q be Q1 minus Q2. Okay, and then we have that Q1 minus Q1 alpha minus Q2 alpha. So the fractional part here, so these two things, the fractional parts differ by some number here. Okay, so they're going to be smaller than, okay, up to some integer, they're going to be smaller than 1 over Q. So up to some integer is less going to be 1 over Q. So this is going to be the integer that offsets these two things, because these two guys are the fractional part of the integers. We're going to subtract off Q here. Okay? So, all right. So now, so this guy here is equal to Q alpha minus P, like so. Okay? So this tells us that alpha minus P over Q, so I'm dividing by P over Q, is less than 1 over Q. And this is less than 1 over Q squared. Like so. Okay? In particular, note that this thing here, this difference here is well, it's less than 1 over, so there's two things we can say. We can say it's less than 1 over Q, as in the original statement up here, which we said that we produced them, so this statement here, right? Notice that if if I just got rid of this Q, since I'm dividing by, this is a positive integer, right? So this thing is smaller than 1 over Q, and it's also smaller than 1 over Q squared, because here, from this part over here, we're using that Q is bigger than Q, right? bigger than or equal to q, I guess we should say. Right, because we're using this part here. And that, okay, so I guess we could say less than or equal to. But then this whole thing is still less than because of this inequality here. All right. So that's the idea. This is, and then why are there infinitely many? There are infinitely many, again, because we fixed q arbitrarily large, and then we can make this approximation within 1 over q no matter what. Okay, so we can make this within 1 over q. Okay, so, and that's how we show that we can arbitrarily approximate rational or irrational numbers with rational numbers using the pigeonhole principle. Okay, and so what I'm going to do now is I'm going to make another video which describes, which proves the things that I owe you. So it's going to talk about how to prove the pigeonhole principle, that there's no bijections. So it's a little more technical and a little less useful, but I still wanted to cover it. Okay, see you in the next video.